Hello, good morning. I'm Amy Heimberger.
And I'm Craig Horbinski.
So today we'd like to talk a little bit about methylation and what that means in the domain of oncology. I will be acting as the interviewer, and Dr. Horbinski will be the interviewee. So Dr. Horbinski, methylation, we commonly use it in the setting of CNS tumors, where we specifically look at methylation of MGMT. And this is a marker for sensitivity to a chemotherapy called temozolomide. But you're not just doing methylation for this specific gene promoter, you're doing more global methylation. So what is the impact of methylation profiling versus standard, let's say, sequencing profiling that patients are much more familiar with now?
Sequencing covers specific hotspots in the genome that we know are disproportionately mutated in certain kinds of brain tumors. And in the targets that we go after have prognostic, diagnostic, or therapeutic significance. Methylation profiling takes a different tack. It's not sequencing looking for specific mutations or copy number alterations. Instead, what it does is, because in addition to that MGMT methylation, it turns out there's hundreds of thousands, really millions of sites across an entire genome that can be methylated, just as little chemical modifications to the DNA. It sounds weird, but actually all of your cells do it. All of our cells do it. Every single type of cell has a unique methylation pattern. Certain spots in the genome are methylated, certain spots are not. This allows the cell to turn on and off certain genes as needed for its particular use. So for example, lung cells are going to have a very different methylation profile than skin cells, than colon cells, than brain cells. Well, the tumors that arise from these different kinds of the tissues also have different methylation signatures according to the other mutations they've got and where they arise in the body. And what we found over the years, the field has found that those methylation patterns produce a fingerprint that can be used to reliably identify not just the tissue type, but also the subtype of tumor that is arising in that given tissue. And this is especially been proven useful for brain tumors, where each different kind of brain tumor, regardless of what it looks like under the microscope, has a unique methylation pattern that clusters with its brethren, its other tumors of similar type. And as a result then, we can feed the methylation data into a computer and determine, okay, this tumor maps to this spot versus another spot, and you can discriminate otherwise two very, very similar tumors.
So with regards to CNS tumors, having been in the field for a while, we started off with a lot of times the pathologists would debate. You'd send a specimen to one pathologist versus another pathologist, and there'd be this ongoing rigorous discussion with regards to it's an oligo or it's an astro, and sometimes one pathologist would say it's this, another pathologist would say it's that, and the treatments are a little different between those two types of gliomas.
Prognosis too.
Yes. So how does methylation help, first of all, distinguish then between these different lineages? How is it superior compared to, let's say, just sequencing, or let's say doing things like looking at very specific alterations like IDH mutation, or staining for, let's say, OG2 or something like that? How is this better than what you guys have been doing all along?
Well, sequencing and histologic interpretation still have a place. They still have a very critical role to play. But what methylation does is it adds another layer of information onto what we've already got. So for example, there's times when, like you mentioned, you can have two different kinds of tumors, and they're so similar to each other that histologically it's hard to tell one from the other. Sequencing wise, they may have certain kinds of mutations that you could find in any kind of cancer, and they don't really help. Okay, it proves that, yeah, this is a cancer. Well, great, we already knew that, but what kind of cancer? Sometimes the sequencing just doesn't tell you. But methylation then can tell you what that tumor actually is, because it's taking a different, much broader scope of data. It's like fingerprinting is a good analogy, but like every person has their own unique fingerprint that can be used on a forensic basis to identify who was where at a given time. Well, we could use something very similar in terms of diagnostics. Every tumor type has its own unique methylation fingerprint. And we're able then to determine what that fingerprint is and whether or not the histology is equivocal, whether or not the sequencing data is diagnostic or not, the methylation is diagnostic.
So we had an interesting case a couple of weeks ago in tumor board where we had a metastasis to the brain, and it looked histologically like everything. And there was a very rigorous, robust discussion during tumor board. We couldn't figure out where it came from. How does the methylation help us figure out where it comes from? Because that's important, because it informs how we're actually going to treat this patient.
Yeah.
Because not all cancers are treated with the same drugs or the same immunotherapies.
Well, that was a very challenging case histologically because it didn't even really look like a metastatic tumor. We couldn't tell it apart from a primary glioma, like a poorly differentiated glioma. That can happen a lot of times with these tumors, is they're so
Undifferentiated.
They're so undifferentiated, they don't really look like any one thing. And then when we stained it with all kinds of immunostains, parts of the tumor stained for almost everything. Like, okay, a part of it stained like lung, a part of it stained like prostate, a part of it stained like glioma. And you're like, well, what is it? It can't be all these things at once. It has to be one thing. So that was a great example. We did sequencing on it, and it showed amplification and mutations of various genes, and you look at it, you're like, well, all right, that really doesn't help us. It proves that it's a high-grade cancer. In that case, we already knew that, but it really didn't pinpoint us towards a specific diagnosis. Whereas the methylation patterns, and this was an interesting case because it was a negative result in this case turned out to be proof. Because our methylation library is very, very good. It's got thousands of cases from primary brain tumors, central nervous system tumors. And this tumor did not match any of those tumors in our library, which by deduction then we are able to confidently say this tumor could not have originated in the brain because it matched nothing in our library of thousands and thousands of tumors, representing almost 90 different kinds of tumors that can arise in the central nervous system. And this tumor didn't match anything like that, not even close. So then we were able to deduce that it had to have been metastatic. And going forward, one of the things that we're now working on is a library to better characterize those kinds of tumors so that we can not only say, yes, did not come from the brain, but we know where it had to have come from. So we're not quite there yet with the metastatic library, although we are developing it, so that we will be able to say, oh, this had to have come from the gallbladder, or this came from the liver, or this came from the lung, or the prostate, or any number of places.
So in addition to identifying, in other words, providing a fingerprint of what the cancer is, does the methylation signatures help the clinicians decide on therapeutics? Are we there yet?
The diagnosis itself can, of course, direct therapy. There's plenty of times when we think it's one kind of tumor and then it becomes another one. Oh, in that case, it did direct therapy because it might require different radiation or maybe even no adjuvant therapy at all. Those sorts of things. So yeah, in that case, it does. But that is one of the areas, that's what's fun about this field in particular, because it's so wide open. So one of the things that we're actively working on as part of the methylation consortium, where we're pulling all of our resources from multiple institutions that are bringing this in-house. And one of our priorities is to figure out, okay, are there specific methylation signatures, for example, that correlate or predict better response to immunotherapies?
What about chemotherapy? Is that also the case, you think?
Yes. Certain chemotherapies for sure, we're going to be investigating as well. Yeah.
So, one could argue, well, can't we just do this with sequencing? Because right now there's a lot of precision medicine. There's academic centers that do precision medicine, which is where you take the tumor, you sequence it, you find certain targets, and then you let patients and their physicians know that they might be eligible for a certain therapeutic that goes after that specific target. And this is done both by academic centers as well as commercial vendors where they identify this match. Isn't this methylation just the same thing as like sequencing? How is it different or better, or what are sort of the limitations of sequencing relative to methylation?
Well, it turns out that, for example, mutations and copy number alterations, gains and losses of certain genes, those are only a couple of the ways that a cancer can modulate its own genome.
Okay.
Methylation is another sneaky one where it can turn off genes or indirectly turn on other genes that are critical for that cancer's growth, for that cancer's response to therapy or therapy resistance. And if you only look at sequencing, if you only look at copy number alterations, you're going to miss those other mechanisms by which the cancer remodulates its own genome. So there could be gene X, for example, whose suppression, whose downregulation correlates with better response to drug Y. Well, if you sequence that tumor and you find no mutations at all in that gene, if you do your copy number scan, you have the whole genome copy number scan, and you find no deletions or other kind of alterations of that gene, you would mistakenly think that that gene is not altered. And that's not true.
Correct.
The gene could be completely shut off by methylation.
Or amplified.
Or turned on indirectly by methylation. This is where things do get kind of complicated, because the tumor could also turn on a gene by turning off its suppressor gene. You know, if there's one protein that turns off another gene, well, cancers are very clever. If they want to turn on a particular gene, they can turn off its suppressor.
Okay.
That's a double negative almost. And so methylation can reveal those previously mysterious alterations.
So one of the things that's always a little bit of an issue, at least for CNS diseases, as a surgeon, a lot of times I can't necessarily resect something. In other words, I can't give you a lot of tissue so that you can really do all of these different analyses on. I give you a little tiny little piece of tissue through a biopsy needle. Is there an inherent advantage of methylation profiling versus sequencing? Because I know sometimes you just don't have enough for the sequencing. In those scenarios, would you have enough for methylation?
Yeah, in those cases, as it turns out, as long as the biopsy has a decent amount of tumor cells in it, relative to non-neoplastic cells, to non-tumor cells, we really only need the standard is about 250 nanograms of DNA.
So much less.
Which is less, yeah.
Relative to sequencing.
Even relative to sequencing. Although sequencing has gotten pretty good at making, getting useful information out of a little bit of material as well. So that's come a long ways, even in just the last few years as far as that goes too. So in most cases, if we can do methylation, we can also do sequencing.
Yeah, because sometimes patients can be very frustrated when the physician comes back and says, look, there just wasn't enough of your specimen to actually sequence. Do you think methylation would be able to resurrect those kinds of cases or assist in the diagnosis?
Yeah, in some cases, in some instances, that is turning out to be the case. Yeah, that we are able to salvage in some fashion a diagnosis. Yes.
Now, I certainly know that there's been a lot of changes in the technology for sequencing, but you still have a significant delay for many patients, although commercial vendors can sometimes be fairly robust about this, where you get the initial path report and then the sequencing data may not come back for several weeks later.
Right.
Is methylation faster, the same as sequencing?
It's a lot of it's economy of scale. So at least here at Northwestern, for example, if we've got a case that was generated in a given week, we will, in most instances, unless something happened, some technical delays, in most cases we're going to have methylation results by the following Friday. So we're looking at roughly 7 to 10 day turnaround on average.
Okay, so about the same.
Yeah, it's about the same. But the key then is, okay, when the cases are resulted, is that diagnosis then integrated with the histology? Are all the factors then blended in to create an integrated, unifying diagnosis? And is that then conveyed to the clinicians? So very often, that turns out to be the delay. More so than even the actual generation of the molecular report, it's integrating it with everything else.
Okay. That's
one thing, and here at Northwestern, we've got a pipeline where we integrate those things very quickly. So I'm signing out several batches of molecular cases per week. So any given case does not sit very long.
So one of the things, obviously, as we move forward is always the expense of doing these kinds of things, these kinds of profiling. For sequencing, some patients have said they've gotten bills $3,000, $5,000, et cetera. And, there's reagents, there's the cost of doing it, there's the bioinformatics. Relative to the technical sort of issues around sequencing, is methylation easier, harder, the same as sequencing?
It's a little more straightforward and technically and less expensive.
Okay.
Because it's an economy of scale. So what happens is when you do a run, we can run 32 samples at a given time, 32 distinct samples. And as long as we load that machine up with 32 slots, by economy of scale, that run costs a lot less than if we only ran 4 samples or 2. And as a result, then we can, by virtue of us having a big volume, which we do here, including a lot of consults, we're loading that machine up every week, usually a couple times a week. And then we're just able to crank out a lot of information, and on a per case basis, it's a lot less expensive.
Okay. Why are there so few academic institutions right now that have it?
Yeah, well, first of all, it's going to be, a number of institutions are in the process of bringing it on. We just happen to be one of the first. But there are a number of other institutions that are working on it. It's just that the process is slow. It's one thing to produce a scientific paper showing, hey, this works. We did thousands of cases and look at this, and that's tremendous. I mean, obviously, those are highly impactful studies. But for an individual institution then to take that research and translate it into clinical use on a routine basis, well, that's a different level of rigor than even a scientific paper requires. So you've got to really, really prove that every single step in your protocol is validated, that you can do everything that other group published. You can recapitulate all of their data, and not just on a technical, like using it in a laboratory setting, but also now bioinformatically, because that's another layer of sophistication that prior assays didn't have. So we've got to make sure that all of our computer algorithms, all of our machine-based learning, that all of that produces the same results that have already been published by others, and that everything aligns internally. So we had to accumulate a bunch of cases that we tested and compared to another laboratory which already had a CLIA certification to do this test. We had to compare our results against theirs to make sure we matched with them, as well as the original study that was published. I mean, there's a lot of layers of validation, which is essential, because then when you're prospectively going into an unknown case, you want to know that your results are indeed reliable. Because now it's not just a research project. Now that it's an individual person whose care is going to be dramatically altered by these results.
What is the proof that this is valid as far as actually identifying the right cancer? What are the key papers that really illustrate this?
The biggest one would be from the Heidelberg, Germany group by Kapper et al. That was published in Nature in 2017. That was the landmark study. Other smaller papers beforehand had suggested that this was a promising way to identify different kinds of tissues and different kinds of cancers, but they're the ones who really took it to the next level, specifically in the context of central nervous system tumors. Thousands of cases. I think they did almost 3,000 cases, plus a validation cohort of their own, showing that, hey, when we take all these cases that had been previously diagnosed, both by molecular and by, of course, histology, by experienced neuropathologists, and we run them through methylation, most of the time the methylation aligns with what had previously been diagnosed. The diagnosis was correct, it confirmed it. But there were a lot of cases, a surprising number of cases actually, where the methylation said, no, actually the tumor is something else.
Okay.
And so the acid test in such a setting is, well, how did the patient do? Did the patient's tumor ultimately behave like the original diagnosis, or did it behave like what the methylation said? And in virtually every instance, it behaved like what the methylation said.
And many other neuropathologists like Dr. Daniel Brett have worked on the World Health Organization criteria for distinguishing different types of CNS tumors. And I believe there's just been a recent update.
The 5th edition, it just came out, yeah.
So are you guys going to have to get back to work on the 6th edition?
Well, yeah, it's interesting because the 5th edition, the most recent one that just came out, was actually issued sooner than it was originally planned. Because normally it's about 10 years or so in between editions. But this one had to come out sooner, had to jump the line, so to speak, because of all the advances in copy number, alterations, sequencing information, all those things. So a lot of the new entities that are in the new WHO book are defined by the existence of certain mutations and copy number alterations. Well, even in this new WHO book that we wrote, the 5th edition, we did mention that methylation profiling can be used to classify a lot of these, really all these tumors, and we kind of hinted a little bit that it's going to be a bigger role in the next WHO book. Now, how soon will that next WHO book come out?
Have they sent out invitations yet?
Well, that's a good question. I'd say at least another 5 years, only because the WHO publishing company, they've got a lot of other different kinds of tumors that they have to address as well.
Yes.
It's not just brain tumors. They've got head and neck and hematopoietic tumors and all these other books that they have to work on. But yeah, I would guess between 5 and 7 years from now, we're probably going to be looking at another WHO book, incorporating a lot of new entities based on methylation profiling.
Now, you and I have spent a lot of time talking about CNS tumors, but is this going to be widely accepted also for other oncological indications, breast cancer, lung cancer? How is this emerging in other oncology domains?
Oh, for sure, yeah. In fact, the next one up is that they're actively working on are sarcomas. These are relatively rare tumors, soft tissue tumors that can be notoriously difficult to classify under the microscope and even to some extent by sequencing, etc. Very, very mysterious type of tumors.
Will it have a role in more conventional cancers like lung cancers, breast cancers?
Yeah, so there's a lot of libraries actively being generated now. A lot, because that's the key. With methylation profiling, you have to have a big library of known cases so that a new case can be compared bioinformatically to the existing library, and that's how you get your diagnosis. Because it's all based on machine-driven learning. And so yeah, we're going to be doing that not just for the sarcomas. That's the next big one because those are so hard to diagnose traditionally, but also all the other conventional tumors. Because what we're going to find is that even if I say, oh yeah, this is definitely a breast cancer, great, and yes, it's ER driven or PR driven or HER2, whatever, fine. We're going to find out that by methylation profile, when you profile enough of these tumors, that new subtypes are going to emerge based on unique little quirks in their methylation fingerprint that will probably have some sort of diagnostic, prognostic, and therapeutic significance. So even in the well-characterized tumors that we know for sure what it is, we're going to have another level of data that we didn't even know existed until we did methylation profiling.
So now we're really talking about research. And where do you think the greatest opportunities for research for our basic scientists lies in the domain of methylation?
Well, a big one that we're going to be looking at very carefully is our certain methylation signatures, for example, with brain cancer. Are certain methylation signatures better predictive of a good response to immunotherapy? That's it's highly likely we're going to find something. If you do enough cases and you follow them over a long enough period of time, we're going to find something interesting. Or other targeted therapeutics too. There's all sorts of things that we're going to be looking at. But the key is to pool all of our resources together, multiple institutions team up, combine our data, right? So, you get a bigger N, a bigger cohort, you get more information out of it. But yeah, I think at least for now, immuno-oncology is maybe the lowest hanging fruit.
So we've gone through quite an evolution of IO markers for response. We started off with basic, T cells in the tumor microenvironment, PD-1 expression, PD-L1, then we went to TMB, microsatellite instability. The list keeps going on and on and on and on. So what makes you convinced that methylation might be much more predictive of some of these previous markers for the IO?
Well, it's the methylation is adding so much data and revolutionizing how we envision these tumors in other regards. There's probably going to be, like we were talking about before, certain genes when they're methylated and they're silenced might make the tumor inadvertently more responsive to immunotherapy or less. It's when you're casting that kind of a wide net. We're literally looking across the entire genome. It's almost like brute force bioinformatics. And if you have the right kind of analyses, and the right kind of clinical data to feed into it, you're going to find something. It's just the odds of us finding something are very, very high.
So it's a much more global interrogation of potentially that tumor microenvironment as opposed to just a single distinct little marker that interrogates one feature of immune reactivity.
Exactly, because it might not just be one specific gene that's methylated or not that is associated with a given outcome. It could be, or it could be if this gene's methylated but that gene is not, and that gene is, and that gene's not, well, the combination then becomes predictive of immunotherapy response, potentially. And that's the sort of analysis you just can't do on a single gene basis. That traditional approach to science won't work in this setting. And that's where, again, the bioinformatics, the sophisticated bioinformatics really comes into play because, computers and computer analyses can pick up those kinds of patterns that we
Can't
can't.
necessarily see, yeah.
And to use another metaphor, we're going to be throwing a whole lot of spaghetti against the wall. Something's going to stick. Something interesting is going to stick.
Anything else you think our audience should know about this emerging technology?
Well, it's now in Northwestern. We're one of the first centers to offer it nationwide on a routine clinical basis for consultations for brain tumors. We're open for business. It's already starting to really change our diagnoses on a lot of cases.